Hello everyone. In this video series, I will be talking about organometallics and its application, and also I will initially I'll start with the various stability of metal complexes and how to count electrons in the metal complex, and what are the various types of ligands that we will be discussing later in organometallics, and also for note I'll be following Elias book, and I will also have the problem solving sessions. So let us start. So the first chapter that I'll be talking about is the 18 valence electron rule. So in this chapter, what we will learn. In this chapter, we will be learning how to count electrons in the metal complexes and what is the basis of, or basically what is the theory behind this electron counting, and how different ligands donate its electron, or we can say share its electron, and what are the hepticities of different ligands, and all different types of ligands we are also going to study, and we are then after studying all of these, we'll be counting electrons for unknown complexes. Let us go forward. So first, there is a term heptacity and sandwich compounds. So what does that mean? So until now, we have generally seen, so basic organometallics knowledge, from that we have seen that there is one ligand that donates electron to the metal. Okay, right? But in some cases, what happens is that this ligand can donate like from one atom to this metal which is donating. Okay, so in that case, we call it the heptacity is equals to 1. But sometimes when the ligand can share its electrons with from more than one atom to that metal at the same time, then its heptacity can be greater than 1 in that case. So those ligands that are capable of sharing its electron by more than one metal, by more than one atom, or we can say by more than one of its atoms to a single metal at the same time. So that is the term heptacity. Okay, so heptacity is one, means there is only one atom by which the ligand can share its electrons to the metal, and heptacity greater than 1 means there are more than one atom in the ligand that can share electrons simultaneously to metal center. Okay, so let us read what is given in the book. A number of unsaturated organic anions. So we know that ligands are generally anions. They can be neutrals as well, but in case of neutral, they should have lone pairs, right? So a number of unsaturated organic anions and molecules such as allyls. Okay, cyclopentadienyl. Let me draw the structure for better understanding. Cyclopentadienyl, and all of these, ethylene and benzene, can bind to a metal in more than one way. Okay, so for example, we are taking the example of allyl. Okay, so here it has one negative charge, so by which it can donate to the metal center, and also here it has lone pair of electrons, that is a pi electrons. By this also it can share to the metal. So in total, how many atoms? Yeah, by how many atoms this allyl ligand is sharing the electrons to the metal? It is for pi bond, you count both the atoms, right? So 1, 2, and from this carbon by negative charge, so 3. So in this case, allylic case, the heptacity would be 3. In case of cyclopentadienyl, so how many atoms can share the electron at the same time? So for example, the metal, I'm drawing it here. So by this carbon, by a negative sign, by these two carbon, by this pi bond, and again another pi bond, so these two carbons. So total of 2 plus 2 plus 1, that is equals to 5 is the heptacity. Okay, similarly for benzene, how many pi bonds we have? So we have 3 pi bonds. So by all these 3 pi bonds, it can share, right? So heptacity for benzene would be 6 now. For each pi bond, there is 2 carbon. So you have to count these 2 carbons per pi bond. Okay. So the different modes are distinguished by the number of carbon atoms participating in linkage with the metal. To be more precise, one has to see how many carbon atoms are present within bonding distance from the metal atom, as I have discussed. The hepto symbol. So this is eta. So this is the symbol for the heptacity. Okay. With a numerical subscript provides the, for example, there has to be some numerical superscript. Okay. So it provides a topological description by indicating the connectivity between the ligand and the central atom. So for example, cyclopentadiene have eta 5, right? For allylic it is eta 3. So for example, if all the 5 carbons of a cyclopentadienyl moiety are equidistant from a metal atom, we term it as eta 5 cyclopentadienyl, right? So this is heptacity. Let us move forward. So let us study the very important and the very basic thing in organometallics to start with is the 18 electron rule. Because without this 18 electron rule, you cannot even think if that complex can exist in nature or not. But by counting the electrons, you can actually say that whether the complex is stable or not, right? So the stability of the complex is governed by this rule. What this rule is all about. So we know octet rule, right? So for octet rule, what was that about? So it was said that the valence bonds, the valence orbitals can accommodate total of 8 electrons. So if that whole valence shell is completely filled, then we can say that the atom or the molecule is stable in nature. But that octet rule was only valid till argon. After argon, things is different because after argon we have d orbitals as well, and with the coming of d orbitals, so d orbitals can accommodate how many electrons? It can accommodate total of 10 electrons by 5 orbitals, each orbital 2 electrons. That is why you are adding 10 to that 8. So that makes 18 electrons, right? So now, since d orbitals are in picture, you now need 18 electrons to fill the valence, right? All these metal complexes, the metal has d orbitals, and hence they need 18 electrons to fill their valence shell, right? So that is what is 18 electron rule. Now let us move forward in this rule. So before 18 electron rule came into existence, we had EAN rule. So what does EAN means? EAN, first of all, the full form is the effective atomic number. So what people used to do before 18 electron rule came into existence, people used to count the electrons of the metal complex, all the electrons of the metal complex, and not just the valence electrons, which was difficult also because it is easy to calculate the valence electrons because the periodic table is arranged in such a beautiful way that you all know what is the valence electron of almost all the atoms. You must know, right? Because of the periodic table arrangement. Now, EAN. So in this case, you have to calculate the electrons. For example, you are given a metal complex and you are set to count electrons according to the EAN. But in that case, you need to count all of the electrons, not just the valence electrons, but 4 of the electron needs to be counted. So in that case, if that whole of the total number of electrons in that metal complex, if it is equal to the atomic number of the nearest a noble gas, then you say that your metal complex is stable. So that is what is EAN. But what is the reason behind the decline, behind not using EAN and introducing a new technique of like saying the telling about the stability of the metal complex, that is the 18 electron rule. So the reason behind this is written here. You can see. So it is evident that the EAN rule invokes the use of the chemically inactive core electrons that results in separate numerical stability standards for each row of the transition metals. For example, for 3D series of metals, when you're counting with metal complexes that are made up of 3D series metals, then the standard numerical value is 36. But for 4D, it is 54. And for 5D it is 86. So this stability standard is different for different series of metal, which was not good. So if you are actually giving some standard number, that if your metal complex has a particular number this, then your metal complex is stable. So that was even easier, because in that case you can bring in uniformity. But in case of EAN rule, the uniformity was not there, because there was different numerical stability standard for different row transition metals. But this is because the 18 electron rule came into picture, and 18 is that numerical standard of stability for the metal complex that all the metal complexes follow, irrespective of the rows, because all the metal complexes needs to fulfill only 18 electrons in its valence shell in order to gain stability. Okay, and how this 18 electrons come from, like which orbitals these 18 electrons will go? It will be NS, N minus 1D, and NP. You can count the number of electrons, right? P for 6 for P, 10 for D. So 10 for D and 2 for S. So total of 18 electrons. Okay. Now, to apply this rule, the assumptions made were that the ligand were Lewis bases and the metal ions are Lewis acids. And the rule states that thermodynamically stable transition metal organometallic compounds are formed when the sum of the metal electrons and the electrons conventionally considered as being supplied by the surrounding ligands equals to 18. So here this orbital needs to be filled, and for this you need 18 electrons. We all know that in the transition metals, there would be like these orbitals will not be all the time empty. With the metals also have some electrons. So these say, like for example, you need to consider x plus y, two variables that needs to be, when you add them, it needs to be 18. So you need to consider that this x is the number of electrons that is initially there in the metal. Okay, and y is the number of electrons that the ligand shares to the metal. So in that case, you need to consider ligands as the Lewis bases and the metal, because it is gaining electron, it is taking electron from the ligand. That is why it is termed as Lewis acids. Okay. Now, let us move forward. We now know the basis of the 18 electron rule. By counting the number of outer shell electrons surrounding each metal atom in a complex, it is possible to predict whether the complex will be stable, and in some cases, whether there will be metal-metal bonds present or not. Okay. And what about this last line? We will be dealing with this line in the later chapters. Okay. For now, you consider, by counting the or by knowing about the 18 electron rule, by following that, you can actually tell the stability of the metal. If the metal complex, the electron comes out to be 18, then you can say that the metal complex is stable. And when the metal complex, the electron count is not 18, then what happens? We will discuss that in the later. In this chapter only we will be discussing it, but later. Now, now the question is, okay, we know that we need to count the electrons of the metal complex, and if it is 18, then the metal complex is stable. Now the question arises is that How do we do that? How do we count the electrons in the metal complex? So there are two methods of counting electrons: the neutral atom counting method and the oxidation state counting method. Both this rule, there is a different way of counting electrons. Okay, in both these two rules, you count atoms differently, but the answer always comes out to be same. Okay, it depends upon you which method you want to choose, which method you are more comfortable with. Okay, what is the difference in two counting methods, that we will be discussing now. Okay, the neutral atom method is more foolproof as it does not require the correct assignment of the oxidation state of the in a metal compound. So now, in order to count electron, you must know how many electrons metal has in its own, because now in case in any metal complex the metal has an oxidation state, but sometimes it is difficult. By looking at the metal complex you cannot directly tell the oxidation state of the metal. So in that case it is always beneficial to use the neutral atom method, where you consider metal to be not positively charged entity, you consider it as neutral. Okay, and in that case you consider that the lone pair contributes to electrons, and also a negative charge also contributes to electrons, and that is how you count the electrons. Okay, but in case of oxidation state, you need to consider the oxidation state well before counting the electrons, which is sometimes difficult, because sometimes it is very difficult to predict the oxidation state of the metal before counting the electrons. Okay, after counting the electrons, you can get some idea of the oxidation state by just questioning the stability of the metal complexes. But beforehand of the counting of the electrons, you cannot sometimes tell the correct oxidation state of the metal center. So it is always good to use the neutral atom method, because in that case you don't need to know the oxidation state of the metal beforehand. However, it is written also, however, the oxidation count method is followed when one has to follow the changes in the oxidation state of the metal center in a reaction. Now, table 2.1 gives the electron contribution of a variety of ligands according to the neutral atom and the oxidation state counting method. So this table 2.1 we will be talking about very deeply, because this is where the key lies. Now, if you know like which type of ligands, how many electrons it is given to the metal, then only you can count the electrons. But so for example, you don't know that a certain ligand, how many electrons it is capable to give, then you cannot count the electron for the metal complex surely. So table 2.1 is very important. Now let us start counting the electrons and also finding the metal-metal bonds. So by metal-metal bonds, you can say that when the electron count doesn't come to be 18, then what are the different consequences you can think of? Okay, so from there you will get to know what is this term. Okay, since metal carbonyl compounds contains the metals in the low oxidation state, there are many compounds that possesses the metal-metal bonds and fall into the category of metal carbonyl clusters. Indeed, the largest and the structurally most complex structure cluster compounds belong to this class. Okay, here the line it is written that metal carbonyl compounds contain metals in low oxidation state. Why? Because generally metal carbonyls, they are L-type ligand, or we can say they are here the ligand is not ionic. Okay, so the metal will not be more positive. Okay, it will be neutral only, or we can say low in the oxidation state. Then that is what it is written. So in such cases, there is this fair probability of forming the metal-metal bond. So let us study to determine the total number of metal-metal bond and find out the number of bonds each metal makes with other metal atom in a cluster. The following procedure is followed. This procedure applies only to those complexes having a nuclearity greater than or equal to 4, less than or equal to 4. The electronic structures are easily understandable in terms of electron pair bond between adjacent pair of atom metal atoms with each metal atom containing 80 electron configuration. So we will be counting the number of, first of all, we'll be counting the number of electrons in the metal complex, and then using that information, we can calculate the number of metal-metal bonds in the metal complex, and also we can calculate the number of bonds per metal in the complex. Okay. But before that, we need to understand, we need to know the counting of the electron before calculating the metal-metal bonds and the number of bonds per metal atom. Okay, so this table 2.1 has listed a lot of ligands that is of importance to this standard of organometallics. For example, carbonyl. So and the electron count is given accordance to both the method, that is the neutral atom method, and also the oxidation state method respectively, and also the formal charge is written. Okay, both the electron contribution and formal charge is mentioned here. Now let us go one by one. So the carbonyls, how is carbonyl look like? So carbonyl has one lone pair in the carbon, right? So that lone pair is shared by the metal atom. For example, I'm writing it here. So this is the carbonyl ligand, has one lone pair. Okay, and that lone pair is shared by the carbonyl to the metal. So whenever lone pair is shared, then always 2 electrons is shared, and 2 electrons is counted. Okay, in both the cases, in the neutral atom method also 2, and in the case of oxidation state method also 2. And these type of ligands are considered as L type of ligand in rod cells. L type of ligand are those type of ligands that donates the electron by the lone pair. So L type of ligands always share 2 electrons by both the types of metal counting. Like neutral atom method also 2, and the oxidation state of electron counting also 2. And the formal charge here is 0. So the ligands with the formal charge of 0 are the L type ligands. Phosphine is PR3. So it also has one lone pair. So it is also L type. So it is also going to share 2 electrons from both the methods of electron counting. Similar with amines also has one lone pair. By lone pair only it is donating here. Okay, but in case of amides, how it is donating? So in case of amides, where N is connected by 2 R only. Okay, you know that N can make like 3 bonds, right? So, but here only 2 bonds is given, for example, here. Okay, so in that case, N has one negative charge. So this negative charge is shared by the metal. So now this type of ligands has a formal charge of -1, and now the electron count changes. So if there is some formal charge, then the type of ligand would not be L, then it could be called as X type ligand. So in that case, how much, if the formal charge is -1, that it has only one negative sign, so this one negative sign contributes how many electrons in total? 2 electrons, right? So if it is 1 electron, then it would have been 1 radical, and when 2 radical, then it is called -1 charge. So that is 2 electrons. So by the oxidation state method of electron counting, you would count the electrons as 2, okay, for a negative sign. And in case of neutral atom method, you will count it by number of charges. Here the number of charges is 1, so the electron donated by it will also be 1. So in case of such amides, the neutral atom method will give the electron count as 1, and the oxidation state of electron contribution will be 2, and the formal charge here is -1, and that is why the ligand is X type. Hydrogen again is H what? Negative, right? Now, if in case of H negative, it is again donating its negative electron to the metal, and that is why it has formal charge of -1. By neutral atom method, you will consider as 1 electron, but in case of the oxidation state method, you would count 1 negative sign as 2 electron. Okay. Now, alkenes. So alkenes is this. So it has how many pi electrons? 2 pi electrons. Okay, so 2 pi electrons means, and also this alkenes is a neutral atom. So the formal charge is 0, and hence the ligand is the L type. So whenever there is L type ligand, I already said before, then in that case of where the ligand is L type, the electron contribution from both the neutral atom methods and the oxidation state method is same. Here 2. Okay. Now alkynes, if it is sidewise, so alkynes also 2. Okay. You can say that alkyne has 4 pi electrons. So it can donate 4 pi electrons. So you can say eta 4 also, but it is written sidewise. Sidewise, you know that here there is 2 pi electrons, but these 2 pi electrons are not in the same axis. They are in the different orientation. So you, in case of sidewise, you can only make bond with one type of orientation of the pi electrons. So 2 electron per pi bond. So that is why the electron counting is 2. Again, here the ligand is L type, and that is why 2 for both the methods. Eta 2. So you are already written over here. Hepticity is 2. So if hepticity is 2, that means it is connected by more than one carbon atom. So in such cases where more than, so here it is 2. So this eta 2 C60 is a neutral entity. C60 is a neutral entity. We know this. So 2 means it is bounded with 2 carbons. So that is why it is giving 2 electrons. Okay. Now the nitrosyl bend and the nitrosyl linear we will be talking about. So these two ligands are kind of very tricky when it comes to counting electrons. Now let us learn how. First of all, let us understand what is the uh, meaning. Like what is the basic geometry of these ligands. So the bent nitrosyl. First of all, I will draw how it looks like. So this is the bent nitrosyl. Okay. So in this case, there it is bonded by the oxygen with two bonds, one sigma and one pi, and one lone pair is there, and it binds with a metal with a negative sign. Okay. So the nitrosyl bent has a formal charge of -1, and by the neutral atom method, it will give only one electron, and by the oxidation state method, it will give as it will be a 2 electron contributor. But in case of nitrosyl linear, so it is all, it will be mentioned in the question. It is binded with oxygen by 3 bonds. Okay, so that is why it has a charge of positive. Okay, and now there is one lone pair in the metal, in the nitrogen, sorry, by which it is donating to the metal. The formal charge of this ligand is +1. Okay, and the number of electrons it is giving, because it is giving by lone pair, so from the oxidation state counting it will be 2 electron donor, but since it is formally positive charge, therefore from the neutral atom method it would be a 3 electron donor. Now the carbines. Okay, so carbines again is a this type of ligand. Okay, so in here it is a -2 type ligand. So it is -2. Okay, the formal charge of carbon is -2. So how many electrons it will give by the neutral atom method? So by the neutral atom method, it will give the number of negative charges, that is 2 here. So it will be 2. But for the oxidation state, for each negative sign 2 electrons. So here 2 negative signs, that is why 4 electron will be counted from the oxidation state method. From and the alkoxide, that is O negative, OR negative. So now it is negative. That is why it will be act as the X type ligand. Now the mu CO. How many electrons? Again, the CO doesn't have any charge. We know that carbonyl is neutral. So it is L type ligand, and L type ligands generally same, it will give the electrons will be, the electron counting will be same for the neutral atom method and as well as the oxidation state method, and it will be 2. Okay, mu alkynes. So when it is given normal alkynes and not written sidewise, so in that case you count this 4 pi electrons. Okay, it is again L-type ligand, so the electron contribution from both the methods will be same. In here, because there is no sidewise overlapping is written, that is why you will count the electrons from both the pi bonds. So that will contribute total 4 pi electrons, and that is why the electron contribution will be 4 for both the methods, because it is L-type ligand. And when it is mu alkyl, so the mu alkyl is R negative. Okay, so R negative means X type ligand. So number of electron contribution by the neutral atom method would be 1, and the number of electron count from the oxidation state method would be 2. Okay. Phosphido. So what is phosphido mean? So by here you can draw the structure, right? It is one metal, another metal. There is a phosphorus bond which is bonded to 2 R atoms. Now we know that phosphorus now has one lone pair and one negative charge. So the formal charge is negative, right? So it is -1, but it is, since it is bonding to, it is mu, so it is bonding to two, it's a bridging type of ligand. So it is bonding here to 2 metals. It is given in the this parenthesis. So it can bind to one metal by this negative sign and by one metal by the low L type. So it will act as a X type ligand for one metal and L type ligand for another metal. So when it will, so how many total electrons? L plus X. So by the neutral atom method, how many electrons? So the neutral atom method, L, the electron counting is 2. For X type, the electron counting is 1. So total 3. But for the oxidation state method, excuse me for this bad writing. So from the oxidation state method, L will contribute 2 here also, but the X type will contribute 2. So the total of 4. So this mu phosphido will be 4 electron contributed from the oxidation state method and 3 from the neutral atom method. Let us move forward. The halogens is X type ligand and hence this type of electron counting. Alkyl we already studied. Aryl is negative. Then it will go X type. Here acyl. Now acyl is again. It is very simple, right? So C double bond O and there is R. So it has to be negative sign and act like X type ligand. Now eta 1 cyclopentadienide. Eta 1 it is written, but then that means cyclopentadienide is like this. Total 5 carbon, and we saw that it can total show up to eta 5 when all these 5 carbons are bonded. So number of carbons by which it is bonding to the metal is the heptacity. Okay, so it is heptacity 1. So 1 cannot come from the pi bonds. Okay, because pi bond always 2 minimum. Okay, so 1 will be coming from this negative charge. So in case of eta 1 alike, it will be formal negative charge always. For the cyclopentadienyl is negative charge only, and it will act as an X type. When eta 3 is given, means 1 by this negative type and 2 by this 1 pi bond type. So here it will be it will act similar to L plus X ligand with the heptacity of 3. When it is eta 5, we already know, right? So it will be L to X type. You can count that accordingly. Eta 6 benzene we already saw. It is a neutral type of ligand, hence the electron count will be same for both the methods. It is 6. Carbyne. So carbyne is -3, right? The formal charge here is -3, and hence by the neutral atom method it will be 3 electron contribution, and by the oxidation state method it will be 3 into 2, that is 6. Thiolate is similar to alkoxide, and it will also act as an X-type ligand, mu H. Now, mu H has again, H is hydride, has a formal charge of -1, right? But it is mu, it is written. That is, here hydride is acting as a bridging ligand. So in that case also, it has only 2 electrons, right? One formal charge it is having. That is, it is having 2 electrons. So maximum how many electrons a hydride can share? Even though it is connecting to two metals, it can only share two electrons at a time. So it will be a 3. Let me draw it for you. That will be very, very simple. Okay, mu h. So this means like this, right? It is hydride is a bridging type ligand. So it is bridging two metals. Now, since hydride only has 2 electrons, so the total electrons can be 2 only. So the formal charge is -1, and that is why it will be acting as X type ligand. Now these halogens, here halogens, when it is acting like a mu, that is a bridged ligand. So let us draw that also. Okay, so it has one minus charge. So this minus charge will be utilized by one metal, but it also has lone pairs, so that will be utilized by other metals, and that is why it is a LX type ligand here. Or we can say how many. So from the LX we can count from the both the that is easy, right? Mu alkoxide also exists, right? So in that way, because alkoxide, because O has one negative and also is bonded with one R, it has negative charge and also lone pair of electrons. So it also acts as a LX type ligand. I hope that now the electron counting is clear to everyone. So what is this? Let us first calculate. So this is one metal complex. Okay. So let us now start counting the electrons from the neutral active method. So from the neutral active method, you don't consider the oxidation state of the metal. So now, how many electrons does ruthenium has in its valence electron? So you need to count that first. Okay. So you can easily get to know by the group number in which the ruthenium is present, right? So it is present in the 8th group. So it will have 8th number of valence electron, and that is why this 8 is written. Now this ligand, it is connected by the eta 3 fraction to the allylic ligand. So it is LX type. So since we are counting the electron from the neutral active method, so LX type ligand will contribute 3 electrons. Okay. It is also connected to 2 PPH3 group. So PPH3 is a L type ligand. So both the PPH3 will count 2 and 2 electrons respectively. So 2 PPH3 will contribute 4 electrons. One carbonyl will contribute 2 electrons. And also, since there is one positive charge, so you need to subtract 1 from the whole. So you are subtracting -1, and the total you will, when you count it, then it is 16. Okay. From the oxidation state method, you need to know first the oxidation state of the metal. So in order to calculate the oxidation state, you must have the knowledge that which type of ligands are present. So this allyl has a negative sign. All the rest of the ligand are positive sign. Sorry, neutral. So plus X, where X is the oxidation state of the metal, has to be equal to +1. So X will be +1 +1, that is 2. So oxidation state of ruthenium from the oxidation state method is +2. So ruthenium +2 has 6 electrons, right? It used to have 8 electrons when ruthenium was neutral, but it is +2. From the oxidation state method, you need to know the oxidation state of the metal. So after knowing the oxidation state of the metal, you need to subtract that number from the valence electrons it originally has. So now it is 6. Then from this allylic bond will act like LX, and in case of LX, the oxidation state method, the electron contribution by this LX type ligand would be 4. Okay, so you add 4. Again, these 3 L type ligand is same, will behave as the same way. That is why 4 from 2 PPH3 and 2 from 1 0. Okay, now in this case, you don't need to consider this charge because you have already considered this charge when you were taking out the oxidation state of the metal. Okay, so now it also gives 16. So see how these two methods are very different by counting, but gives the same result. Now let us count another last metal complex which is given here. So this is iron. So you need to count out this metal complex, which is iron complex. So from the neutral atom method, iron has a D8. So it is a D6 S2 system. It is a group 8 atom. So hence 8. Now it is cyclopentadienyl, right? So cyclopentadienyl is L2X type ligand. So from the neutral atom method, how many electrons? L2, that is 4 plus X type, that is 1, that is 5. So 5 from each the ligand. So 5 plus 5, 10. So 10 plus 8, 18. Now consider the oxidation state method. Now you need to first calculate the oxidation state of this iron. Now this cyclopentadienyl is X type, L2X type. So X is negative. So one negative it has, one formal charge it has. So one formal charge from each of the metal, and the whole is 0, right? Nothing is there means 0. So -1 plus X, but and rest is equals to 0. So X is equals to again plus 2. So you need to have 8. Sorry, 6, because iron is plus 2. And how many electrons? It is L2X. So L2, so 4 electrons from L2X, also 2 electrons, that is 6 electrons from each cyclopentadienyl ligand. So total 6 plus 6, that is 12. Again, it is giving 18. Right? Hope I am very clear by counting the electrons. Okay. So let us now calculate the number of metal-metal bonds. Now, how do we calculate the metal-metal bond? Now, first of all, until now we know how to count electrons, and what we have also studied various types of ligands like that exist in organometallics, and that we are going to deal with. Okay, so how to calculate the metal-metal bond? Now we are going to study. So before that, there are some thumb rules that needs to be followed when you're actually calculating the metal-metal bond, and this is where I'll conclude this lecture. So you need to first determine the total valence electrons in the entire molecule. That is the number of valence electrons of the metal plus the number of electrons from each ligand in this charge. Say it is A. Okay, first you calculate the total number of valence electrons. Okay, the way you are calculating it till now, you need to count the electrons, valence electrons of the metal complex. Okay. Now after that, you need to subtract this number from n is equals to 18, where n is the number of metals in the complex. So you will be given the name of the complex, right? So for example, in that case, number of metal is 3. So in that case, what you will do? So in case of metal is 3, so for each metal you need to have 18 electrons. So if the number of metals in a complex is 3, then you need to have, or say n in general, then you need to have n into 18 electrons to fulfill the stability factor, right? So there from there n into 58, n into 18 comes into picture. Okay, but you need to subtract the total valence electron that is there in the metal from n into 18, where n is the total number of metals in that metal complex. Okay. Now, what you have to do, you need to calculate n into, you need to calculate n into 18. Then you need to subtract the total number of valence electrons, and then you need to divide by 2. Okay, so that will give you how many bonds, because 2 electrons form 1 bond, right? So that is why you need to divide it by 2, because you need to count the number of bonds. You need to get number of bonds from this calculation. So each bond has 2 electrons engaged. So it is the number of electrons that you counted. So that is why you need to divide it by 2. Okay. If the number of electrons is 18, so if it is 18, then there is no metal-metal bond. Already the metal complex is stable by itself. But if it is 17, so this indicates that there is one metal-metal bond. If it is 16, then it indicates that there is 2 metal-metal bonds and so on. Okay, I hope I am clear. So this is the table 2.2, which actually is again important. So it is counting some of the total valence electrons, so that if you get to know this, then you can actually calculate the total number of valence electrons of an unknown complex. So let us start from chromium. Now you need to calculate the total number of valence electrons from this metal itself. So chromium is how much? It depends upon you that which method you are going to opt. Okay, I am opting the neutral active method because there you don't need to know the oxidation state of the metal. Okay, now chromium. It is 6 plus 6 into 2, that is L type ligand, 6 into 2, that is 12. So 12 plus 6 is equals to 18. Okay, so similarly, I think it is very easy for you guys to do it. Now let us count it for FeCO whole 4 2 minus. So iron is from the neutral method is 8 and L type carbonyl ligand 4 into 2 8 again. Okay, so 2 negative is there, so you need to add 2. Okay, so here also 18 you get. Eta 5 Cp2 cobalt. So Cp is, we know what Cp is, right? Now each Cp we know eta 5 it is given, so it is giving, it is L to X type. Okay, so now from the neutral atom method it will give 6 ligands, 6 electrons from each Cp. So since there is 2 Cp, so 6 into 2 6 into 2 is 12, and now it is cobalt. So that is equals to 9. Sorry, 7. Okay, so that is equals to 7, and then you need to minus 1. So that gives 18. So similarly, you can do for rest of the compounds for table 2.2. I hope I'll end this section here, and then we will go to metal-metal bond calculation in the next lecture. Thank you.